the years, engineering was limited to a real plane, one that we can draw and understand with real-life physical representations. But we were limited. How can you, for example, calculate the square root of -9? The bringing about of complex numbers not only answered this question, but also revolutionized many fields within engineering, amongst them electricity. Chemical engineers rely heavily on the use of complex numbers when exploring electrochemistry, a field which is extensively used in, for example, fuel cell research. Ms. Dina Ibrahim is a PhD student here at UCL, whose research focuses mainly on fuel cells. She will now explain how complex numbers help her in the calculations for impedance, a vital part of this field.
I'm Dina, I'm a PhD student in the Chemical Engineering Department at UCL, and I work in the Electrochemical Innovation Lab, also known as the EIL, and my work is on supercapacitors. So what I do is I use cellulose from trees, and I try to produce electrodes that can work in supercapacitors to produce energy out of green materials. Part of the research work on electrochemical impedance spectroscopy, which actually involves some Nyquist plots, and this is how actually the computer deals with the complex numbers. I don't do that personally, but the Nyquist plot actually plots the imaginary numbers versus the real numbers to get the impedance and hence the resistivity of the system.
We will now look at an example of how complex numbers can be used to calculate the previously mentioned impedance, whilst only using information from the voltage and the current. So, the current and the voltage of a specific AC circuit system is given by the following equations. Remembering that E represents the voltage and I represents the current. So, the voltage is of 5.8 volts and the current is of 5.8 amps. The frequency of the voltage is 61.1 Hz and that of the current is 35.1, and there is no phase difference. So we're asked to find the impedance at time equals 0.5 seconds. To solve for each of these, we need to find E0 and I0 respectively, and the angular frequency for both the voltage and the current. Since the phase difference is of 0, we can forget about that term in the current equation, and we are already given t, which is 0.5 seconds. Since we already know I0 and E0, the only thing we have to calculate is the angular frequency. Now how do we do this? You might recall that the formula for angular frequency is given by 2 pi f, 2 pi times the frequency. So using this equation, for voltage we get 383.9 radians per second, and for the current we get 220.54 radians per second, implying that both the equations can be summarized as follows once the appropriate numbers are plugged in. Recalling that Zt equals Et over It implies that the 5.8s will cancel and we will only be left with powers to subtract. Hence, the impedance can be summarized by e to the power of 81.68j. Recalling Euler's formula, which is e to the power of theta j equals cos theta plus j sine theta, implies that substituting in values for theta yields cos of 81.68, which is very near 1, and sine of 81.68, which is very near 0. So our final answer is 1 ohm. Thank you very much for watching.